cohere. That is in the sense that they are the same phase with respect to each other, fixed phase, and even the same amplitude. That's one way of doing it. And the reason you can do that actually is because fundamentally, where did this light come from? Each atom that's radiating light, by some means or other, it's sending out a wave train. Let's say it's a light wave. It's sending out a wave train, and actually that wave train comes to us, and it has a finite length. But each of those finite wave trains can hit this pair of slits, and part of the wave train goes through each slit. So each atom separately, his own little wave train can go through. So even if this is white light, or as we can see some other discharge lamp or fluorescence, pulse by pulse, emission by emission, each of those reaches here, and they are coherent with each other. So this wave train can interfere with itself. It can't interfere with the wave train of another atom that emitted earlier or later, or even the same time, but maybe with a different polarization, maybe with a different frequency slightly, even if they're identical atoms. But it can interfere with itself. That's what I'm trying to say. Each atom sends out a wave, and the wave train is finite. In other words, an atom will send out light in, let's say, 10 to the minus 8 seconds. And let's say 10 to the minus 8 seconds, and at the speed of light, meters per second. Here's a simple example. So the wave train, if you look at the length of this wave train, if that was emitted 10 to the minus 8 seconds, it'll be, let's say 10 to the minus 8 cancel, it'll be about 3 meters. So a typical, if that is the lifetime during which light is emitted from an atom, the wave train might be 3 meters, 3 yards. So if you send it through here, it'll be about 3 yards long, and it can interfere with itself as long as you don't. Here's what we do. We imagine that wave train as a new source of waves of the same wavelength. Let's say about this. This is a very important idea, that each point on the wave, every point on the wave, sends out a wave train as though it were a point source. So this point sends out a wave train as though it were a point source. Every point does. This is known as Huygens principle. Let me see if I always have difficulty spelling his name. I don't know where the U's and the Y's go. H-U-Y-G-E-N-S. Huygens, H-U-Y-G-E-N-S. Huygens, he's a Dutch physicist, a contemporary of Isaac Newton. And in fact, Huygens had this idea that this is the way to look at how waves move, and in particular light. And as it happened, Isaac Newton, who's more famous than Huygens, disagreed and said that light is not a wave. He said it's a particle. The reason was that if you look at the shadow of something, it looks pretty sharp. And if you have an obstacle and you look at the shadow looks pretty sharp. So he said, well, that's because these are little particles of light, and they make a sharp edge here. He should have looked a little bit closer, because as a matter of fact, the edge is not exactly sharp. It'll turn out. The edge, actually, there are little extra fringes here. If you look really closely, sometimes you can sort of see when you look through things. You will be doing actually in your lab. I think you're going to do it with a hair. You're going to look at the light as bent by a hair, and you'll see that it's not exactly a sharp edge. But Newton thought it was. Maybe he needed glasses or something, or better glasses. But Huygens thought it was a wave phenomenon, and he posited that each point of a wave would emit wavelets, as he called them, and that's how waves would propagate. It's a very prescient idea, because we've talked about the fact, for example, of electromagnetic radiation, how it goes through a medium. It comes in as an electromagnetic wave, it grabs the atom, it shakes the atoms re-radiate radiation. So Huygens was very right. He said a wave comes in, each point of the wave is going to shake an atom, and it's going to propagate as a wavelet. But that atom is really re-radiating waves, little wavelets. So he was really right. The way to look at the way a wave propagates, you take each point and consider that each point is sending out a little wavelet. And that's your new wavefront. And even if the light should hit a medium at an angle, what's going to happen is that when this hits, it's going to send out a wavelet at a speed depending on the speed in the medium. Whereas, you see, the light here comes later and will send a wavelet out, but then you get a new wavefront that looks something like this. So what you get is that if the light comes in at this angle, let me see, the light is coming in at this angle, its wavefront will turn toward the normal, because this part here is retarded with respect to this. So the new wavefront will be in this direction. This is a little bit tricky construction. The light is coming in, say like this. Here's the normal. Here's our angle of incidence. Because this hits first, it slows down. The wavefront turns toward the normal. See the difference between this big angle here and this small angle here. And the way you can understand that, the way Huygens says, is because when this wave hit this material here, it started to propagate by sending out little wavelets, but their speed is less than the speed in this medium. Let's say this is air and glass. This is how Huygens would explain the refraction of light into a medium. He says when the light hits this medium, it starts to propagate its little wavelets, but they are going slower. In the meantime, this light here has gone faster, and so this front will be more advanced, which turns the wave front toward the normal. So he could explain the bending of light in refraction by this Huygens construction. So this is the basic idea. The two ideas that you have are, to explain all these phenomena in this chapter, is that you have the Huygens principle of each point on a wavefront sends out wavelets. So you just follow them. And then they interfere. They add up. And where they cancel, and where they add, they add. And that explains pretty much everything. Now, before you leave today, I'd like you to take a look. Well, let me divide this first. If you follow those two ideas, let's consider what happens, for example, if you have two slits. You have your wave coming in, and part of it goes through one slit, but this slit acts as a source of circular waves, which propagate out. And let me go on here. I think I have a demo set up here a little bit. Maybe this one. Hope it's set up here. See. Yeah, okay, that's nice. All right, this is precisely, you can see it, can you? Or should we put the light out? It's a source, and what's happening is that the waves are coming, they're passing through this slit. I wonder if I can make it, let's see, slit width. What's happening, you see each of these, when it passes through here, they're coherent because they all started from the same source, and they're creating a new circular wave, but this circular wave interferes with that one's circular wave, and it gives a maximum in the center, but there are places where this one's minimum hits that one's maximum, and so they cancel out, and they give you less intensity over here. And that's the idea. You start out with coherent waves, you superpose them in various places, and if you change the path length, like this one, to get to this place, it travels a little bit further than this one, and so the waves would start out over here in step. Because this one had to go further, it lags behind, and so when it lagged behind, its peak overlapped the next one's trough. So you create this phase difference by making a path difference, okay? And you get this, what's called a diffraction pattern. It's again, the superposition of two ideas. Namely, there's a Huygens wave coming out of this point, this slit, and and at certain places, there is a phase difference which produces an interference. Namely, the waves get out of step with each other. I think I can make these slits closer together, or let's say, that's more, let's say less. What happens? Well, you can, I think you'll see that the peaks start to move further out. So we can play with this, and we'll derive how that works. Yes, question? Sir? You want to see with two lights? Okay, let's try. Where is one light, two lights? Oh, this may complicate the story quite a bit. Let's see what happens. Yeah, now we have two lights, and each of them is supposedly they're in phase, that is descending out at the same time, but where this guy's beam overlaps this guy's beam, you can get cancellations. So that's really a mess. So I avoided that at first. But back here, well, I guess there's more or less a single wave here, and each of these is acting. So you can get interference. Here, electronically, you can make two waves in phase. With light, it'd be very hard to do. Even lasers, it's hard to get them to be exactly in step. But with sound and what waves you can control mechanically, you could probably get them to be coherent. That is, same amplitude, same phase. With light, it's much harder. You happy with that? Okay, let's see. We go back to one. Do we go back? Oh, that's one slit. Well, this is interesting too. Let me get one light though, because it's a little bit too confusing. Here's one light. Now, what you can see is that even with one slit, when it passes through, what we'll see is that different parts of the slit can interfere with each other. Granted, they're all in phase over here. But what happens if I look over here? You see the light will have traveled from this edge of the slit to here, and the light will have traveled from this edge of the slit to here. And if those are sufficiently out of step, they'll cancel out over here. And in fact, you get a peak here, but you'll also get a null, where there's a cancellation of the waves coming from this edge and from that edge. We'll get into that too. But let me derive, if I have a minute, I have 5 minutes. Okay, let me derive just the one quick formula for this, the two-slit story, and that is very simple. The idea is that you're trying to find a place where the light coming from this center here arrives at a certain place. But what would it take for the light to be annulled, in other words, dark, at that place? Well, the idea is you have a wave going out, but if the wave is 1/2 wavelength delayed, its peak is going to arrive when this one has a minimum. So that this peak will fill in that minimum, give you 0. So what I want is this length, this distance, to be equal to, or the extra length, equal to a half wavelength. In other words, if the ray coming from here is 1/2 length shorter or longer than that, then it will be delayed by a half wavelength, and it'll come in. This peak will come in on the trough of this one. So the difference is that this spacing. What kind of notation do I use here? Oh, I used D in the wrong place. Okay, let it be changed in the path length, say, and let's call that separation here D. So if this is D, we can get the angle through which this delta L is equal to. This is like a hypotenuse, so it's opposite over hypotenuse. That is d sine theta. So we have lambda equals 2d sine theta. Is that? Yeah. Okay. So this would give you the first minimum, or lambda over 2 equals d sine theta. Or if there were n whole wavelengths plus this, n lambdas plus a half wavelength would give you this too, because a whole wavelength doesn't do anything to you. So it would be lambda n plus a half equals d sine theta. Will give you a minimum. So that's the first minimum if you have a two-slit pattern. Now the demonstration I wanted to show you is, while we have it, the point is that you can add up even more slits. You can have slits, and all you really ask for is that the extra path length is n lambda plus a half, n plus a half lambda. N plus a half lambda is the path difference to give you the first minimum, or to give you a minimum. When n equals 0, that's the first minimum. So all you need, you see, is a periodic structure of slits, such that when the Huygens idea is that each of the atoms radiates, or each of the slits radiates, you can get a peak or a minimum, depending on when they interrupt. Now here we have an example, which is a simulated crystal. You can't see from there, but there are little metal balls stuck in this styrofoam in a square array. And there's a whole stack of them, so we have sort of a three-dimensional crystal here. And each of those represents kind of a slit, because when the microwaves hit it, let me turn them on. When the microwaves hit the balls here, each of them acts as a Huygens source, and they re-radiate. And if they come back to this horn in sync, you get a peak. On the other hand, if you turn the horn, the waves will travel yet different distances, and they may not reinforce each other. They may cancel each other. And this is the principle of X-ray diffraction, which is a very powerful tool for measuring crystal structures. I mean, I guess you know the story of DNA, where Watson and Crick managed to get the X-ray diffraction pattern from Rosalind Franklin. You know the story? Very famous story. And they could recognize from the pattern of where the maxima were in this X-ray pattern. They saw that it must have been a spiral structure. They were sufficiently good at crystallography pattern. Rosalind Franklin was very good at preparing samples and making measurements, but she didn't quite leap at the idea that it was a spiral. And so Watson, who saw this data, ran back and quickly published. And Rosalind Franklin was a little upset, needless to say. But they published the paper afterwards with the data. You know, they announced the structure, and then Rosalind Franklin gave them the data. So is this thing working? So there's a major reflection. So in some places, the waves, there are electromagnetic waves coming out of this tube. They're being hit onto these metal balls. The metal balls are re-radiating like little Huygens oscillators. And if they come back in phase, you get a nice big strong effect, whereas over here not. So from this pattern, from the angles, and knowing the wavelengths, you can get the separation between the balls. In other words, you know the crystal structure. And that's how we determine the crystal structures of materials. It's a very big business up at the advanced light source. This is what they do up there. They have X-ray sources to study. So what you have to get, though, is, very importantly, the lambda and the d have to be somewhat similar, or else this is not easy to work. See, when lambda and d are roughly the same size, then sine theta is a reasonable angle. You can't have sine theta, for example, more than 1. So you couldn't have a lambda much bigger than d, because you see sine theta is lambda over d. So if lambda is much bigger than d, this couldn't work. So you have to have lambda less than d. So for atoms in a crystal, the great thing was that they recognized the wavelength of X-rays was less than the likely spacing between atoms. So in 1910 and 12, this was just after X-rays were discovered, they realized that you could use X-rays, whose wavelength they didn't quite know, but they knew it was very short. And they knew roughly how far apart atoms were, because they knew Avogadro's number and the volume and so on, and you know how many, and you could figure out roughly the spacing.